My name is Mark Bly. I'm the Group Head of Safety and Operations at BP, and I led the company's internal investigation into the events surrounding the tragic accident aboard the Deepwater Horizon on April 20th, 2010. As you may know, the Deepwater Horizon drilling vessel was stationed in the Gulf of Mexico on the Macondo well. The rig crew was in the process of finishing work on a deepwater exploratory well when a series of events culminated in a blowout of the well, explosions and fire on the rig, the tragic loss of 11 lives, a number of serious injuries, and one of the largest oil spills ever seen. This video summarizes the findings and analysis of this investigation team. As I review these, it's important to keep in mind the goals of the investigation. Our team was assembled immediately after April 20th in order to identify the critical factors underlying the accident. Our mandate was to determine what happened so that BP could take whatever steps necessary to prevent a similar accident from ever happening again. Our purpose was not to apportion blame or liability, but rather to learn, recommend areas for improvement, and share our lessons with others. While I believe that we had sufficient evidence to reach the findings summarized here, our work was limited by a lack of direct access to some witnesses and to certain physical evidence. I will be presenting our findings factually, but it is important to note that our purpose was not to create a record that would serve as the definitive or final word on what happened. The investigation team consisted of more than 50 internal and external engineering specialists with expertise in various aspects of deepwater drilling and exploration. We worked over a 4-month period examining all available evidence. This visual portrayal of our key findings is best viewed in the context of the report, which describes more fully the basis for findings. The findings were based on witness accounts, analysis or modeling, as well as engineering drawings, real-time data from the Deepwater Horizon, physical evidence, and testimony gathered from governmental inquiries. The team's report was delivered to the board and BP's top management. They are sharing it publicly in order to keep the public informed, to assist with the government's various investigations, and to ensure that BP and the industry can learn from the accident and take appropriate actions going forward. To determine what led to the tragedy, it's important to first understand the events that occurred aboard the Deepwater Horizon leading up to the accident. This short animation depicts the best understanding the team was able to reach about the chronology of key events as we understand them today. This is an animated reconstruction of the tragic accident aboard the Deepwater Horizon on April 20th, 2010. Specifically, this narrative has been developed to illustrate what we determined were the key events related to the accident. The animation contained in this narrative is representative and for illustrative purposes only, and has not been drawn to scale. The Deepwater Horizon was a dynamically positioned drilling vessel whose construction was finished in 2001. It was designed to drill in water depths up to 10,000 feet. The vessel arrived on the Macondo location on January 31st, 2010, to finish the exploratory well that had been started earlier by its sister vessel. The riser and the BOP were installed successfully. 4 casing strings were installed over a 2.5-month period. Our narrative begins on April 9th, 2010. The final hole section of the well was drilled to a total depth of 18,360 feet. The long string production casing was installed. During the afternoon of April 19th, the cement job started. Cement is used as a barrier to seal the wellbore from the reservoir sand. Nitrified foam cement was pumped into the annulus and non-foam cement was pumped into the shoe track. At this point, the pump pressure was bled off and it appeared that the check valves in the float collar were holding. It's now the morning of April 20th. The wellhead seal assembly was installed and tested. A positive pressure test, which is the first integrity test of the well, was conducted by closing the blind shear rams and applying 2,700 psi of pressure. The test confirmed integrity of the blind shear rams, the seal assembly, casing, and top wiper plug. The shoe track, which also plays a key role in isolating hydrocarbons, is not tested because of the presence of the top wiper plug. It's now early afternoon. The drill pipe was run to 8,367 feet in preparation for the negative test, which was the second test of the well's integrity. The test's purpose was to place the well in a controlled, underbalanced state to test all mechanical barriers. It was conducted by displacing some of the mud in the well with a spacer, followed by seawater. After displacement, the upper annular preventer was closed. An attempt to bleed the system down to 0 psi was made, but fluid in the riser was leaking past the annular preventer. It's now 1708. The hydraulic closing pressure for the annular preventer was increased to 1900 psi in order to create a tighter seal against the drill pipe. The riser was filled with an estimated 50 barrels of mud to replace the volume that had leaked past the annular. At 1727, the drill pipe valve was opened and the pressure reduced to 0 by bleeding off 15 to 23 barrels of seawater. It's now 1735. The well site leader advised the rig crew that the negative test procedure needed to be conducted on the kill line to meet permit requirements. The drill pipe valve was closed and the testing reconfigured for flow to be monitored on the kill line. At 1752, the kill line valve was opened. Based on eyewitness accounts, somewhere between 3 and 15 barrels of seawater were bled off. The kill line valve was closed and the drill pipe pressure gradually increased. It's now 1842. Seawater was pumped into the kill line to confirm that it was full. The kill line was routed to the mini trip tank, and less than 1 barrel was bled from the kill line. The flow stopped. The kill line was monitored for 30 minutes and showed no flow, but the drill pipe pressure remained at 1400 psi. A discussion about the source of the 1400 psi took place. It was explained as a phenomenon called the bladder effect. The test was deemed successful. It's now 2000 hours. As part of the normal operations to temporarily abandon the well, the crew began to displace the remaining drilling fluid with seawater. To start this operation, the annular preventer was opened and the well returned to an overbalanced condition, preventing further influx into the wellbore. The displacement continued as planned and the well went underbalanced at 2052. This means the pressure in the well dropped below the reservoir pressure. The well started to flow. It's now 2101. The crew was emptying the trip tank, which likely masked any flow indications on the flow meter. At this point, with constant pump rate, pressure should have declined as the heavier mud was being replaced with lighter seawater. Instead, drill pipe pressure increased by 100 psi, indicating a problem with the well. Analysis of real-time data shows that a 39-barrel gain was taken by 2108. It was then time for the sheen test on the spacer, which is done in order to check that there is no free oil in the fluid that will be discharged to the sea. The pumps were shut down when the spacer reached the surface. A sheen test was performed, and the spacer was determined to be suitable for discharging overboard. The drill pipe pressure increased by 246 psi in 5.5 minutes while the pumps were off. The fluid returned from the riser was routed to the overboard dump line. During this period, our modeling suggests that the well was flowing at an estimated 9 barrels per minute. Displacement of the mud with seawater resumed at 2114. It's now 2131. All mud pumps were shut down. An estimated 300-barrel gain has been taken. Over the next 5 minutes, the drill pipe pressure increased by 556 psi. Rig personnel discussed the differential pressure on the drill pipe. In the next 2 minutes, it appears an attempt was made to bleed the drill pipe, possibly to investigate the differential pressure. Over the next 20 minutes, a series of critical well control events occurred, ending in the order to abandon ship. It's now 2140. Mud overflowed onto the rig floor. A minute later, the mud shot up through the derrick. The diverter was closed and flow was diverted to the mud gas separator. At about the same time, the rig crew appeared to close an annular preventer and drill pipe pressure increased steadily from 338 psi to 1200 psi over a 5-minute period. Mud and hydrocarbons discharged onto the rig and overboard. Activation of the annular preventer appears to have failed to seal the annulus. It's now 2147. The first gas alarm sounded. A cloud of gas spread, setting off other gas alarms. There was a roaring noise and the vessel vibrated. The drill pipe pressure rapidly increased to 5,730 psi, which is thought to be the result of the BOP sealing around the drill pipe, likely after activation of the variable bore rams or the annular preventer fully sealing. 1 minute later, the combustible gas cloud reached the aft starboard quadrant of the main deck and probably entered the air intakes for the engine room. Gas also dispersed under the deck and into the engine room enclosures. The main power generation engines went into overspeed. Within another minute, electrical power was lost and there were 2 explosions. The first occurred at about the same time as the power loss. The second occurred an estimated 10 seconds later. The second explosion appears to have taken place under the main deck in the aft starboard quadrant of the rig. The associated blast pressure wave traveled forward and caused extensive damage to the starboard side, potentially damaging the MUX cables, which allow the vessel to communicate with the BOP. The hydraulic line which powers the BOP may also have been damaged. The fire and explosions may also have caused damage to the surface drill pipe equipment, resulting in hydrocarbons flowing to the surface through the drill pipe. The valve on the drill pipe was left open, exposing surface components to high shut-in pressure. While the BOP had closed around the drill pipe, it did not seal the well, and the subsequent loss of power may have resulted in the rig drifting off station. The drifting rig may have broken the BOP seal around the drill pipe and allowed hydrocarbons to continue to flow up the riser. One or a combination of these events ultimately allowed the fire to be continually fed. It's now 21:52. Over the next 5 minutes, personnel attempted to shut in the well and disconnect the lower marine riser package from the BOP stack. The emergency disconnect sequence for the BOP was activated from the bridge. While lights changed on the control panel, no flow was observed on the flow meters. It appears that the emergency disconnect system did not function. The lower marine riser package failed to unlatch from the BOP, and the BOP did not seal the well. With the Deepwater Horizon unable to disconnect from the well, the order to abandon ship was given at 2200 hours. This animated chronology has shown what we believe happened. Now we'll turn to an analysis identifying the contributing factors. As you'll see, we concluded that there was no single action or inaction that caused the accident. Instead, we found that there were 8 interrelated and contributing factors that led to this tragedy. The first 2 findings of the investigation relate to hydrocarbons entering the well. We believe that the evidence shows that both the annulus cement barrier and the shoe track barriers did not isolate the hydrocarbons, allowing them to flow up the wellbore. The next 3 findings stem from evidence that the rig crew did not observe or recognize that hydrocarbons had entered the well before appropriate steps could be taken to contain them. The negative pressure test conducted in order to confirm well integrity was incorrectly accepted. An influx of hydrocarbons was not recognized until it was too late to prevent the hydrocarbons from reaching the surface because they had already entered the riser. And well control response actions failed to seal and regain control of the well. Our 6th and 7th findings relate to evidence that hydrocarbons came up through the riser and were dispersed across the vessel, creating the conditions for them to ignite. We found that the well flow was diverted to the rig's mud gas separator, causing gas to be vented onto the vessel rather than being diverted overboard. Then, the vessel's fire and gas system did not prevent hydrocarbon ignition. Our 8th and final finding was drawn from evidence relating to the blowout preventer. With the loss of well control and subsequent explosions and fires, the BOP did not seal the well. Each of these findings is explained in greater detail throughout